Alright, so we are continuing our class on solubility. So let's say for instance I have this to be a liquid, a containing vessel, sorry, and this containing vessel is having a liquid, water. It's having water inside it. Now let's say at some point I put in solutes inside this solvent, which is the liquid, and this solvent enters this, just like this. It can enter it in this way, it can enter anywhere. But notice that it did not fill up the, like the solutes I added did not fill up the solvent. So at this point I can say that ionic product is less than KSP. Now, since it's less than KSP, what we are focusing on in this case is just at this point, I will just say that at this point, I have not even started talking about, should I say, KSP. At this point, there is no need discussing KSP. All I just have in this case is simply ionic products, or should I say, my solvents. Now, at the point where I have, for example, this, let's say this is water again. Let's say this is water. Let's say this is water. And at some point, I add solutes in this, and it come and occupy this, occupy this, occupy this, occupy the whole solvent. At this point, I say that ionic products that will be inside, that will form from the solutes here, will be equals to the KSP. Is that? At this point, I say that ionic product is equals to KSP. You can see that at this point, it has reached like a point of saturation. So solute is equal to solvent. At this point, anything I add can no longer dissolve. So at this point, this is where we say that it has become saturated. So ionic product equals to KSP. But at this point, no precipitate will be formed. No precipitate is formed. No precipitate. Now, let's say I have another situation where I add water inside this containing vessel. And let's say this is water. Let's say this is water. And I have this. And I have this. Inside this water. I'm trying to make you understand. You don't divide the water or use anything. I'm just trying to use this to create a reasoning. Now I have these solutes. I have these solutes. Now it has gotten to the point of saturation. That means that the solid here is concentrated. Like in this case, it's now concentrated such that I don't need to. At this point, we also have K. This K stands for equilibrium. At this point, we've reached equilibrium. But let's say as it dissolves, it has reached saturation, I come and add more solutes. You see that the more solutes I add, the more ionic products I am having. So what will happen is that these ones that I'm adding now, because it has reached saturation point, it will now become super saturated. Now at this super saturated state, what will happen is that these ones that could not dissolve will just come here and settle. So it will come and settle. So at this point, we say that precipitate is formed. So at this point, we say that ionic product now is greater than KSP because you have more solutes. So when ionic product is greater than KSP, precipitate is formed. So precipitate is formed. So if I know this, this gives me a general understanding of what we are going to do here. Okay, now see. Let's take for example, I have lead, determining the solubility. So to determine calculate solubility, what I'll first of all do is to, if you're determining solubility, you first be giving KSP. You'll be giving KSP, that is the solubility product. So in this case, notice that lead is existing as PPI2. So it's going to dissolve, and when it dissolves, it will form an ionic product which is in aqueous solution. So 2 plus and minus. Notice that it has to be balanced. So I said here, writing a balanced chemical equation for the solubility equation is very important, because the solubility depends on the stoichiometric ratios or coefficients. KSP can be determined from solubility products. So notice that in this case, I said let S be the solubility of the compound. Now I have S for lead. So this is still solubility equation. S for this. You can use X. I can also write it here. I say you can use X, Y, K in place of S. But I'm using S to stand for the initial of solubility. So I now say substitute S into KSP expression for the ionic product on the right hand side. So inside the KSP expression, remember that with KSP solubility product, look at the KSP expression here. So inside it, you just carry all the S, or you say all the things that you have for S. Notice that in the solubility expression that I properly wrote here, how it should be, replacing it with S. When I change it to S, so because I don't know it, so I will just carry it now. Anywhere I see that particular compound, I substitute. So see 2S in the, I carry this 2S and put for I here. It becomes 2S raised to power 2. Then I carry the S here and put for lead. It becomes S. So that is what I got here. Then this is KSP. The value of KSP is given to be 9.8. So we try to solve. So you see that 2, this is 2. 2 square is 4. S square is S2. 2 square is 4. S square is S2. Then this is S here. So S square times S becomes S3. Then times 4 becomes 4S3. So equals to this. So making S subject of the formula, you have now cube roots. That is the same thing as saying let 4 divide both sides. This 4 will go. Then making S subject of the formula, you take the square root of both sides. So cube root of both sides. So S becomes cube root of everything here. When you do it, you get this as your answer. So it's the same thing with having this. Notice here, I have AB, a situation where I have AB a solid, and on the solution, this thing means reversible. You remember we are dealing with mixture. So when you combine mixture and they form compound, each retains its composition and physical properties. So if you decant or you separate it using separation technique, it can still give you back whatever solid you combined, each of them respectively. So here, if I have solid, if it dissolves, A plus B minus, in this case, it gives me this ionic product. I can replace with S, so that KSP becomes S square. While a situation whereby I have AB square, notice that I just did this for teaching sake. Let's say I have a situation like this where I have calcium OH2. This will simply give me, for solubility expression, it will become CaOH2, reversible reaction where I will get Ca2 plus OH minus, then I'll have 2 beside it. So this is the solubility expression or solubility equation. Now when I want to write the KSP, I will have this to be KSP, because at equilibrium, first of all, at equilibrium, K will be equals to Ca2 plus, then plus 2OH minus all over CaOH2. CaOH2, sorry. Now remember that this is a solid, is constant, at equilibrium is constant. Nothing is entering, it's constant, it's not dissolving again. So when it cross multiply and multiply this, that constant is what gives us KSP. So KSP will simply be Ca2 plus, then OH minus. Now what's solubilities KSP is telling you is that most textbook you just see it raised to like this, and then they will come and say raised to power 2. Raised to power 2. But I want you to know, I want you to get that idea that if this is having a coefficient, as you raise it to power 2, you also multiply it by 2. That is why I'm going to leave my own like this. You also multiply it by 2. So let's say we have 0.111 solubility given for any of this. So you multiply that thing by 2, then raise it by 2. So when you multiply by 2, whatever it gives you, take the square of that value, you get your answer. So this is what you're going to have in situation like this. So if I have A, B, X, it's going to be the same thing as saying A, that is KSP, sorry, is going to be A plus then XB raised to X. And this is going to be minus. So this is what you calculate for the solubility product. While assuming I am giving KSP and I want to calculate the solubility, I'll simply call this now, let's say S. Then because this one has X here, I will call it XSX. And when you times this now, this becomes, at the end of the day, this now becomes on this side, S, this is 2x now, so S square, and notice that it's having the power of x. So let's say, for example, I use 2 here. Let me use 2 here so it doesn't get confusing. So this will now be S2, and this will now be S raised to power 3. And notice that it's carrying x here. Then this x will come here. So equals to KSP. If I want to now find the solubility, I'll divide both sides by x, so that this becomes KSP over x is equals to S3. Now, take the cube root of both sides, and now have S is equals to cube root of KSP all over x. This will be my answer. So that is the same concept I used here to show you a situation where I have something like this. So this is more like assuming I have AB squared. So I'm taking it, let the ion be 2 plus for this one. You get this. And if I have AB raised to subscript 3, I have this, then I have this. So I'm taking it that the ion here is 3 plus. It can be 2 plus, it can be 1 plus for this one. But this one will always be this way. It will always be this in this format. So I now did another example where I said calculating solubility product. When solubility of ionic compound is known, solubility is the one on the right hand side. Its KSP can be determined. Example, at 25 degrees C, and I forgot to tell you, so usually solubility happens at 25 degrees C. It's the dissolving, that is the temperature, the heat. So it can be more, but you know that the application of temperature or increased temperature makes room for it to dissolve faster. So solubility of lead fluoride is found to be 0.64. Calculate the KSP of lead fluoride. So if a question is given as, in this case, gram per liter, take it to mean the mass or gram. When you find mole, take it to mean mole per liter. So I'll just use this gram given to me to find the mole. Notice that density is directly proportional to mass if you think of it. So as density is increasing, mass is increasing. So you need to always know in some cases where you use density to mean mass. So mole equals to 0.64. Then I divide by 245.2 gram to get 0.026 mole. So make a balanced equation. So I separate this. Now this becomes lead one side, and it gives me this ion on the solution, 2 plus. Now fluorine, remember, notice that it has a subscript 2, and that subscript goes to the coefficient when we are dealing with the equation of the solubility. Now for KSP equation, I will now have it to be. So I normally tell students, you know that I did this thing without putting the 2, so that you remember that this is how they always give you KSP. You don't carry coefficient and put inside KSP. But you need to always see it in your mind that for whatever you have in the solubility equation, even when you are doing the KSP, you should have this 2, that 2. So times whatever mole you have for this. Then you still raise it to the power. So see, that is what I did here. 2 times the mole. Then I raise it to the power. Then whatever I get here, whatever I have as the mole of this, still times the two of them. Now when you times it, you get the KSP. So that is for KSP. So in our next class, what we'll do is more of solving questions, especially textbook questions related to this.